Welcome back. This is the second lecture on molecules. And so today we're talking about bonds, which is very exciting. Let's take a quick review of what we just covered in the previous video. We went through the periodic table of the elements, the atomic number, the electrons and the neutrons, and we find that typically when we draw their model, we draw atoms as having an equal number of electrons and protons, such that they are not charged. We also looked at the shells, and that's going to be important in this lecture, the shells of the electrons. Now, this is a pretty gross simplification of what electrons really do, which I think you should check out in your chemistry class. But what we describe them as is having a first shell that takes 2 electrons, and a second shell that takes 8, and a third shell that takes 8. And electrons, or atoms, I should say, are stable, the most stable, when they have an outer shell that's full. It's not that they're unstable when it's not full, it's just that if they can fill it, they will. How's that? Now let's take a look at bonds. So how is it that atoms, I'll just call it ways in which atoms stick together. And it's pretty interesting that there are 3 primary classes of bonds. And they're ordered in opposite directions that I would order them, but the first one is called a hydrogen bond. The second one is called an ionic bond. And the third one is called a covalent bond. So what we're going to use for each of these is a couple of 2 or 3 atoms and allow them to stick together. And this is sort of a weak and temporary bond, and it only occurs in water. And this is in between water molecules, right? Ionic bonds are mainly due to caused by, I'll call it electrical attraction of positive to negative, okay? And these also tend to dissolve in water. And for this one, we'll be talking about the famous NaCl, which is table salt, all right? And then the third one is the covalent bond, which is very strong and is basically doesn't break down unless something breaks it. So if you were to look at how strong they are, now hydrogen would be a 1x, this would be a 10x for those, and it'd be a 100x for covalent. So they're really different in their nature. So I'm going to begin with covalent bonds and work my way back, okay? Let's return to our oxygen structure that we looked at in the previous lecture. And this is sort of a terrible, cheap model of oxygen that I'm going to use, because remember from the periodic table that oxygen has a weight of 16, it has an atomic number of 8, so that means it has 8 protons, and I'm going to draw it with 8 electrons, which is just like that one there. So I'll draw it quickly as I can. It's going to have 1, 2, 3, 4, 5, 6, 7, 8 protons, and 1, 2, 3, 4, 5, 6, 7, 8 neutrons, right? And then I'm going to put that first ring with the 2 electrons around it in the second ring, and I'm going to very carefully draw this so that oxygen has on the outside 1, 2, 3, 4, and I'm going to draw the other 2, 5, 6 over here. I don't expect you to be able to draw these. That's for your chemistry class. But I expect you to understand the idea of the electrons on the outside. What happens, we notice that we're missing 2, right? We're missing 2 electrons in the outer shell for it to be completely stable. When oxygen gets next to another oxygen, 1, 2, 3, 4, 5, 6, 7, 8 pluses, and 1, 2, 3, 4, 5, 6, 7, 8 neutrons, and then that looks like this. It has 2 in the middle, and it also has in the next shell, I'm going to draw it like this. This is how it does it. It actually ends up putting 1 and 2 right there. And then 3 and 4, 5 and 6 and 7 and 8. Now, the drawing that I've just made has 2 oxygen, right? This is oxygen here, and this is oxygen here. And we had 6 in the outer shell, but if we allow them to share 2 pairs of electrons, right, 2 pairs equals a double bond, okay, 1 pair is a single bond. That means these things become something that actually travels around. They go around the oxygen over here, and they kind of make like a 3-dimensional figure 8 around both molecules. So the way I think about it is that sort of holds those 2 molecules together because their electrons are largely shared in their outer shells, right? So when you share electrons, it makes a very powerful force holding those 2 together. It's called a covalent bond. There are single, there are double, and there are triple covalent bonds. That's pretty crazy. If you look at it at something like nitrogen, which has a 5, I should draw this back in black, in the outer shell. The outer shell is 1, 2, and then 3, 4, 5, and then it shares 3, 4, 5 with another nitrogen, right? Woo! So they share all of those things in their outer shell. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So now if you count up each one, this has 1, 2, 3 bonds, right? So that makes a thing called N with a little 2, which is 2 N's together, triple bond. In this case, for oxygen, this is O2, which is a double bond. We have the double bond here and this one here. So these are called covalent, and they don't really fall apart unless something makes them fall apart. So most of the time, they kind of stay together. So that's a super strong bond caused by sharing. Most of the compounds, that is the multiple kinds of atoms brought together in a much larger molecule comprised of different atoms, those will all be covalent bonds, almost all of them. Okay. Next, I'm going to move to the ionic bond. Okay, so let's go down and take a look at that. And for the ionic bond, I'm going to use 2 molecules that are called sodium and chlorine. Right? I'm going to run up to the table and take a look so I get their numbers correct. Sodium is located here, and it has an atomic number of 11 and a weight of 23. So and chlorine has a 17 and 35, okay, approximately 35. So it's going to have 17 and 35. So when I draw the sodium, it's going to have 11 protons. Whoops. I'm just going to, I can't draw all the protons, there's too many. So it's going to have 11 positives, and it's also going to have 12 neutrons, okay? That's just mass, doesn't matter too much, but you should know it's there. When I draw the 11, it's going to look like this. The first shell can have 2. The second shell can have 8. But then it's full, right? Now I've got 10. I need to get 1 more. So in the outermost shell of sodium, I have 1 single electron. And when I draw chlorine, I'm going to have 17 pluses and 18 neutrons. I think that's the right one. And then, of course, I'll have 2 on the inside. Now, how am I going to get to 17 electrons? I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. That's 10. I need 7 more. So 7 more is 1, 2, 3, 4, 5, 6, 7. So now you can see when these 2 things are next to each other, there's this really odd thing. And that is that on this side, right, this, I should draw this electron here, we're short 1, right? We'd love to have 1 right there. And you can see that in sodium, you have an extra. So what ends up happening is that the powerful electromagnetic force of chlorine strips chlorine, and I know the term stripping, but it strips away. Chlorine strips the electron from sodium. And what we say is that it steals it. So it's not sharing it, it actually steals it. So it actually moves over here and becomes part of this molecule over here. So now it's going around and around over here, right? And not going around over on the other side. As a result of this taking of that electron, now sodium has more protons than electrons. So sodium becomes an ion, which we call sodium plus, and it has a positive charge of 1. Okay, and we look at the chlorine now has more electrons than it does protons. It's got 18 electrons, so chlorine has a negative charge. Becomes chlorine negative, and it has a negative charge of 1. And as you have heard, opposites attract. And so opposites attract. So they stick together. And they stick. And so the ionic bond is really just formed between a positive and a negative charge as a result of the theft of an electron. And that makes NaCl, which we know is table salt. There are other kinds of salts that do this kind of thing, but table salt is famous because, of course, it dissolves in the water when you put it in there. Let's move on to the last kind of bond. You know, I'm going to refer you in this case to my structure of water video. Oh, I can't possibly do that. I'm going to shortcut it here and make it kind of quick. I do have another video about the structure of water. And I'm going to draw an oxygen here like this. Whoa! And remember, it has 8 positives and 8 neutrons in the middle. And in the middle of that, it has 2 electrons. And then it has 6 electrons on the outside of that. 1, 2, 3, 4. And I'm very intentionally going to put them right on there and right here, okay? Because those are the ones I want you to watch. When water is formed, it has 2 hydrogens and an oxygen. Now, you know each hydrogen has an extra one, right? Because it doesn't have 2 in the outer shell. So the hydrogen looks like this. It has just a +1. In the middle, that's the proton. And then its electrons on the outside, it has 1 electron, and then it wants to share 1 with water. So that makes a covalent bond. And what I should really draw that as is take the circle off of there, take this string off of here. I'll make it look like this, which is that. And the same one happens over here. H has +1 on the inside. It actually has 1 electron, which it shares 1. Now, if you count water, oxygen's electrons, it has, I use the red dot, it has 1, 2, 3, 4, 5, 6, 7, 8. And each of the hydrogens now has 1, 2, and 1, 2, so they're stable. And now you have a water molecule, which I've drawn in slightly different sizes of the different parts here. So I'm going to try to make them more equal. That looks very nice. All right, and now these are covalent bonds, so that's important. This is covalent because they're shared, and this is covalent because they're shared. All right. What is interesting, though, is that now the size of oxygen is much larger than the size of hydrogen, because hydrogen is basically just a proton and electron, but the oxygen is relatively enormous to the other two. And as a result, when you're sharing something, I don't know if this has ever happened to you, you share something, like apparently you're sharing it, but you're not really sharing it equally. And so these things just spend a lot more time around oxygen, and occasionally they go around hydrogen. but they spend more time around oxygen. So the electrons in the shared covalent bond spend more time with oxygen. It's partly because oxygen's bigger, partly because it has a really strong electronegativity. It strips them off and holds them for longer. This causes the hydrogens to be slightly positive. Whoops. Yeah, slightly positive. And oxygen, which is holding on to electrons more time than half the time, is slightly negative. And we write that by a little d plus and a little d minus. It's not really a d. Let me write it. I can do better than that. It's a little like this, little thing that says Greek letter d. So what I'm going to do is put the little d down here. Oh, I keep wanting to make big d's. I'm going to put a little d down here, and this becomes -1. And these guys have a little d of +1. It's not a full charge. It's just a little d of a charge, like a little d charge. So this is +1. So what has resulted now is that the hydrogens are slightly positive, right? And the oxygen is slightly negative. Okay, and on this particular end of it, it's negative here at this end, right? Not at the other end. So as a result, the molecule becomes what we describe as polar, which means it is slightly charged. Okay, and if you want to think about it this way, if you look at this little structure, it does kind of look like a little, a happy little bear that I like to call the polar bear molecule. As a result of the polarness of the molecule, if you draw molecules that are water, we often draw them schematically like this, and we make these little ends positive and the chin negative. I can't resist putting eyes on this thing, so I'm going to go ahead and do that. But all that means that when they're next to each other, the chins and the ears come together and they line up. And you'll always have a chin next to an ear, and an ear next to a chin, and a chin with ears, and an ear, and then an ear with a chin. It's like this. So water molecules stick together, and each place that this happens, where the ear and the chin get together, and the chin and the ear get together, and the chin and the ear get together, we call that a hydrogen bond. It's a temporary bond. It's more like an attraction. It happens for a fleeting moment, then they break free. As a result, water molecules get very close together, and this results in water cohesion, where water sticks together in things like water drops. And it also makes something like a meniscus. Instead of being a flat, when you put water in there, you can actually make it bubble over the top of a glass. And it also makes a thing called adhesion, where water sticks to other things. Well, it likes to stick to other polar molecules. Cohesion sticks to self. This is also called water tension. Water tension, T-E-N-S-I-O-N. And when you see water tension, you just kind of want to make an exclamation point and say water tension. But that seems so stressful. I really prefer thinking of them as polar bears.